Well, welcome to our first evening lecture for this age group, and it gives me great pleasure, thanks to the WMCTC and the Royal Society of Chemistry, to welcome our speakers tonight, Doctors Mike Batham and Rob James from the Open University, who are going to give us a talk entitled Magic Molecules and the Magic of Oxygen. It's a shame that obviously we can't be in the lecture theatre live because they do some fantastic demonstrations, but hopefully we have the next best thing and you're able to see them online. But hopefully, as this spans quite a year range group, there will come a time when we can actually see them live in the lecture theatre. But just a couple of points. They will be taking some polls or asking. It's going to be a bit of an interactive presentation. And when they ask questions, if you put your responses into the chat, and then I can kind of read them out as well. And then after that, as we get towards the end of the presentation, if you do have any questions, again, if you put them in the chat, and then we'll answer those later on. Well, without further ado, thank you very much. And it gives me great pleasure to welcome Robert and Michael. So thank you very much.
And Maria.
And Maria, I do apologize. Sorry, Maria, I do apologize.
That's okay, that's okay. Thanks, Mark. So hello, everyone. It's great to be here. Nowadays, everyone talks about distance learning, especially in the last year. But can you believe that the Open University has been doing this since 1969? More than 50 years, the Open University started offering to those who could not attend traditional campus universities the opportunity of studying a degree. In our early days, lessons and course materials were delivered through the post and television programs. But of course, now all our courses are online. We continued having this unique partnership with the BBC. The Open University co-produces content for radio and television. I'm sure you all have heard of TV programs such as Blue Planet and Forensics, the real CSI, yes, just to mention a couple of examples. You may wonder how we can provide our students with the laboratory experience required when you are studying a science degree. So back in the day, the OU sent home experiment kits to our students, but now, making the most of latest technology, OU students can remotely control state-of-the-art equipment in our labs from their own homes. And next, Mike is going to tell us a little bit more about home and online chemistry experiments at the OU. Over to you, Mike.
Okay, welcome everybody. And as you can see on the slides, we used to send out what was effectively giant chemistry sets, and the students would carry out the experiments at home. Unfortunately, because times have changed and it's very difficult to transport chemicals by post or by courier, we decided to go online. And if we have a look at the next slide. So we started off with filming experiments. If you look at the top right-hand one, you can see, I'm sure you've all used it in the labs, the stop clock and a digital thermometer. And we did a thermodynamics type experiment, which we filmed. And then that was replayed on originally VHS, then CDs, and then we worked our way to online. Then we worked on simulated experiments, and on the left-hand lower one, there you can see the chemical kinetics experiment. And here we're looking at rates of reactions. And we did this by getting real data and filming a simulation. So the students carry out a simulation. But we wanted to go a step further and get students to actually control real instruments. And on the top left hand, you can see a picture of our infrared spectrometer. So it's a Fourier transform infrared with a powder autosampler. And if you look at the next screen, you can see the controls. You can actually decide which sample you're going to run. And we've got a webcam, and you can see the sample going into the diffuse reflectance autosampler. And then it produces the standard infrared spectrum, and then the students can download it and plot it using Excel or a graph plotting program. And then right at the bottom on the right, that's one of our most recent ones, and that is an auto titrator. So the students can do a titration live, and the experiment runs for 58 minutes. And people say, well, why doesn't it run for an hour? Well, the last 2 minutes, it washes itself out, cleans itself, and then dispenses the next sample for the next student to do it. Because you know what happens, you forget to clean it out because the phone rings just as you're finishing your experiment. Okay, should we have the next slide? We also have this open science laboratory where some of our early experiments, you can actually log on and have a go yourselves. And one of the first ones that I worked on is the flame test. And all you need to do is to log on and give your details, and you'll get a pass, and you'll be able to have a go at doing the flame test online and have a look at how we do our online experiments. But it's not just chemistry. You can see we've got biology experiments, we've got geology, you can even do astronomy experiments. So a whole wide range of science experiments you can do. Okay.
So as well as having access to virtual labs and remotely controlled lab equipment, OU students can attend a short residential lab schools at our campus in Milton Keynes. And we can also bring students close to the action, no matter where they are, by delivering interactive live web broadcasts from our teaching labs. These are known as labcasts. One of my jobs at the OU is leading the presentation of an introductory interdisciplinary module called S111 Questions in Science. And as part of S111 teaching, Rob and Mike deliver a labcast about the fascinating chemistry of oxygen. So today, because of restrictions, it's still difficult for us to get into the labs. So what we've done in this presentation, we have included some videos from one of our previously recorded labcasts. So let's start by briefly discussing what chemistry is and why you will want to learn chemistry. So chemistry is often said to be a central science discipline, and indeed, chemistry is so ingrained into other disciplines, biology, geology, astronomy, just to mention few. It is really important that any scientist consolidates a solid background in chemistry. Chemistry explains the world around us. Chemistry studies the composition, the structure, properties, and change of matter. And as you know, matter is anything that has a mass and occupies a space, and everything that is made of matter is a chemical. So we are chemical beings. We all use chemicals and perform chemical reactions every day without thinking much about it. Like any other natural science, chemistry starts with an observation. In our case, the observation of matter. And our building blocks at the microscopic level are the atoms. So next, Mike will be discussing how big is an atom and what analytical techniques scientists use in the lab to see atoms.
Okay, let's go back in time to 500 BC. And here we meet Democritus, who was a Greek philosopher. And you can tell he's a philosopher. Here's a painting of him, probably not correct, but he has a beret and a goatee beard, so he must be a philosopher. And it's like the cliche of all scientists wearing lab coats. Not all scientists do wear lab coats, but we chemists do, because we like to keep our clothes clean. Anyway, what he said was if you cut something in half again, and eventually you get to something you can't cut anymore. And the Greek word for not cut is atom. And it wasn't really until the 19th century that scientists were working with gases and electricity and found that actually Democritus was true. The smallest particle of an element is indeed an atom. And then in the latter 20th century, we developed powerful microscopes. And here you can see images of atoms, and these are gold atoms, and they are measured using a scanning tunneling microscope. And the distance from the left hand to the right hand is 3 nanometers. So that's 3 times 10 to the minus 9 of a meter, or 3,000ths of a millionth of a meter. So they are very tiny, and we can't see them with our eyes. But the development of these type of microscopes enabled us to engineer in very small spaces and develop the microchips and the mobile phones and the things that we use today and we take for granted have come about because of the ability to engineering in the nano scale. Okay.
Okay, so another thing
you,
that we, yeah, thanks. Okay, so another thing that we cover in our labcast, and we've done in this talk in the past when we've done it live, is look at the properties of gases or the gas laws. And some of the scientists who were interested in gases in the 18th century, one of whom was Robert Boyle, and he was interested in the effect of pressure on a gas. And he came up with Boyle's law, which says that the volume of a gas is inversely proportional to the pressure. And we think we'll demonstrate it. And the way we're going to demonstrate it is actually use some stills, some photos we've taken from one of our lab casts. So we have a bit of apparatus here. In fact, this isn't our apparatus. This is something similar to what Boyle, would have used. It's a pump designed by Robert Hooke. Mike, you know something about that this time?
Yes, so Robert Boyle and Robert Hooke developed the first ever vacuum pump. It was a glass sphere with a gas tap similar to what you have on the burette, and a pump which was driven by a handle. So you turned the handle and it created a vacuum. And they demonstrated it using a pig's bladder, which obviously we couldn't do today. So we're going to use a balloon, which is much more friendly to animals.
Okay, so this is our apparatus. You'll see there's a big, thick-walled conical flask there held by a clamp. It's got a bung in the top, and you'll notice the rubber tubing, which is coming out the side there, that leads under the table. You obviously can't see it on the photo, but that leads to a vacuum pump. So what we're going to actually do is suck the air out of the vacuum pump. But as Mike said, inside the flask, we've got a couple of balloons, and you'll see they're only kind of partially inflated with air. So the question we're going to ask you, and we're going to try and do this on a poll, I think, if it works, is this. Can you tell us that when we pump the air out of the flask, would you expect the size of the balloons to increase, decrease, or stay the same? Okay. So hopefully, if you can stick your answers in there. What we will do in the meantime is talk about another one of the gas laws, another scientist who was interested in gases, a keen amateur balloonist called Jacques Charles. Mike, do you want to say something? Oh, no, actually, we better do this first, haven't we? I'm sorry, I'm going completely out of order, not to worry. So there's our starting point with the balloons. I don't know if you've got any answers to the poll at all.
We haven't yet, but if people want to put A, B, or C in the chat, then I can read them out.
Yeah, we just need a letter from someone.
Just a letter. It's not difficult. It's anonymous, and we're not going to.
No, we're not picking on anyone or anything like that. It's just if you just want to.
Oh, someone said A.
Okay.
A, 3 A's.
I can't remember what A is. A was increased. Okay, that sounds good. That sounds good. We'll go with A, shall we? Let's just go ahead with the photos. There's our starting point. So we're going to suck the air out of the flask. Oh, the balloons are getting bigger. Suck some more air out of the flask. Bigger still. And there we go. That's Boyle's law. So those of you that answered A, congratulations. You're right.
Okay. So the next person is this a French scientist called Jacques Charles. And he said that for a fixed mass of gas at constant pressure, the volume of the gas is directly proportional to its temperature. So V is proportional to T. So once again, we're going to use our old friends, the balloons. But this time, we need a very cold liquid, and we've chosen liquid nitrogen, and that's at minus 196 degrees Celsius, and it's in a thermos flask, as you can see there. And when you put the balloons in, you'll see that they actually shrink. So you can see the orange one was the same size as the yellow one, but when we put it into the liquid nitrogen, it shrunk. And then when we took it out, you can see it's really tiny, but we give it 30 seconds, it warms up, and you can see the balloon has expanded to its original size. And sometimes the balloon makes a big bang, which is part of the live one that we can't reproduce here really. Okay, on to the next slide. Yes, so air is a mixture of gases, and you can see we've drawn a pie chart to give the composition, and the biggest slice of the pie is nitrogen at 78%. Then our favorite, oxygen, makes 21%, and then the others make up argon around 1% and carbon dioxide 0.04%. But when Boyle and Charles were around, the carbon dioxide level was only 0.03%. And it's increasing with time because we're burning fossil fuels. And the more we burn fossil fuels, the more carbon dioxide we produce. And so some environmental scientists think that this will have adverse effects on the climate. And we can see melting of glaciers and melting of the polar ice caps. So this is one of the drivers for trying to move away from burning fossil fuels and looking at other ways of generating electricity. Okay, but it wasn't always like this. Around 300 million years ago, oxygen levels may have been as high as 27%. And the result of this was everything took advantage of the greater oxygen concentration, and it grew bigger and bigger. So this is a fossil from 300 million years of a dragonfly, and it's the size of a seagull. It's actually massive, and it's not just a one-off. There are lots of different fossils that they found of this size. And of course, the creatures that lived on Earth were large. The dinosaurs, they were massive, and the trees and the plants and everything was much bigger. And when they died, the trees and the plants decayed, and they produced the fossil fuels that we use today. But it's a finite. We're not going to go back to 27% oxygen. So another reason why we need to look at alternative fuels.
Okay, so yeah, so we're returning to oxygen now. Who discovered oxygen? That's the three names that are usually associated with the discovery of oxygen are a Swedish scientist called Carl Scheele, an English scientist, Joseph Priestley, and Antoine Lavoisier in France, who in fact was the first. People tend to believe Scheele was the first to discover the oxygen, but he didn't publish his results very quickly, and Priestley did similar experiments and did publish his results quicker and kind of took the credit first. However, there is a theory that it's actually none of these three. Most textbooks will tell you it's Scheele, Priestley, or Lavoisier, but it might actually well be someone else a long time before these scientists. Look, starting with Priestley himself, this is a picture of his apparatus, the big trough there in the middle called a pneumatic trough, various tubes and jars. And you'll notice at the front there's a kind of inverted jar, and inside that jar there's a mouse. And this is sort of his most famous experiment. What Priestley did, he took a mouse and he heated it in the using the sun and the magnifying glass. And the mouse was quite happy. The reason it was happy is because it wasn't just a mouse inside the jar. There was also a chemical called mercury oxide. And if you heat mercury oxide up, it actually produces oxygen gas. So the mouse was able to survive. So the mouse was breathing the oxygen gas, and also Priestley, he had a sniff as well. And he said the following, he said, "I fancied that my breast felt peculiarly light and easy for some time afterwards. Who can tell but that in time, this pure air may become a fashionable article in luxury. Hitherto, only 2 mice and I have had the privilege of breathing it." And that's sort of what he wrote in his notebook. Maybe he was years ahead of his time, because we found not so long ago a bar in Leicester Square which sort of sells oxygen, maybe not today for obvious reasons, in canisters, and it's designed to sort of perk you up. all perfectly legal. And it said, and the advertising material to go with it said it's a pure source of energy. Oxygen stimulates the senses, invigorates you when you're tired, and it's available on its own or as a part of a cocktail. So they say it's a perfect mixer with vodka, but we never tried that. Okay, but going back before Priest's experiment, before Shaler's experiment, there were scientists who actually heated a chemical called potassium nitrate, also known as saltpeter. And if you heat potassium nitrate up, it actually produces oxygen gas. So what we've got here is a couple of close-ups, 3 close-ups from a demonstration that we do in one of our Open University modules. On the left-hand side, you can see potassium nitrate, which at room temperature is a white salt. But if you heat it up under the flame of a Bunsen burner, it forms a molten liquid, obviously, melts rather. And you can see bubbles of oxygen or bubbles of a gas being produced. And in the other 2 photos, we demonstrated that it's oxygen gas because we're dipping in a glowing splint there. And you can see on the right-hand side, it bursts into flame. There's a sort of a purpley colour there. That's really because you've got potassium metal involved, which burns with a purple lilac flame. Okay, so that's the experiment. So if you heat potassium nitrate up, it will produce oxygen gas. And this was exploited, some people think, by a scientist, I don't know, about 2 centuries before Priestley. Around about 1620, there was a Dutch scientist, in fact, more of an engineer, called Cornelis Drebbel, who produced oxygen by heating saltpeter. But more than that, his engineering side led him to build a submarine, the first ever submarine. This was this is a depiction of it taken from a chemical education journal. There were 12 oars people inside rowing away, and this is underwater, don't forget. But they managed to survive because on board there was some potassium nitrate which was being heated, and you had a source of oxygen gas. And so they tell us Drebbel managed to sail his submarine along the Thames. I think it was from Westminster to Greenwich. And there's even rumours that the king at the time, King James I, was on board as well. Okay, that may just be a story, who knows? But anyway, so Drebbel probably was the first person to really discover oxygen and put it to a good use. I think now, this is Maria. I think, do you want to introduce this?
Yes. So the 2 major variables that determine the phase of matter, as you know, is temperature and pressure. So a change in temperature and or pressure may cause matter to change from one phase, gas, solid or liquid, to another. So at atmospheric pressure, the boiling temperature of liquid oxygen, this is the temperature at which the transition between gaseous and liquid phases occurs, is minus 183 degrees Celsius. So in the next video, Rob and Mike are going to make liquid oxygen using liquid nitrogen that has an even lower boiling point than oxygen at minus 196 degrees Celsius. So let's watch the clip. Fingers crossed that
Rob is going to show us an easy way of making a liquid oxygen based on its physical properties.
Okay, so what kit have we got? Well, it's actually very simple. We've got a fizzy drink can that's empty, a funnel through the hole, and a dish to sort of collect whatever we're going to make. Don't forget, in the dewar, as we showed you a moment ago, we've got liquid nitrogen, minus 196 degrees C. What we're going to do is pour it into the flask. Now, hopefully, based on what Maria's just told us...
Try and pour it in.
Yeah, Mike's going to pour it in. The oxygen should condense on the underneath or on the side of the drinks can, with a bit of luck. Now, it's quite difficult to see it. Yeah, if you just want to put a bit more in, Mike. This is very cold, so you'll notice Mike's wearing the protective gloves.
Yeah.
Okay, so with a bit of luck, we should see a few droplets of liquid oxygen starting to appear. There we go. There we go. We'll just let them build up a little bit. What we're going to show you now is actually quite an unusual property of liquid oxygen, of oxygen in general. That's its magnetic. Okay. Now, what I've got here is a very powerful magnet. Okay, this is a neodymium magnet, very powerful. Now, I think we might need a bit more in there. We're not producing much oxygen, Mike, so just a touch more. Okay, it's definitely falling. You may see little globules chasing around on the dish. That's much better. Yeah, we're making some now. Now what I'm going to do is just tilt it up there to you, and hopefully you can see if I hold the magnet underneath. Come on, there we go. Can you see how it attracts the globules? I'm just going to try and pull them towards myself. Whoops, there we go. We've been playing around with this all day, trying to make this as visible as we possibly can. It's not that easy, but hopefully you can see somewhere in there globules of oxygen. And I'm going to try and do it this way as well very quickly. You see the oxygen there. Hopefully it would. Do you want to add some more, Mike? A little bit more. We'll try and make a touch more. This is actually an important property. For instance, the magnetic properties of oxygen is used as the basis of detectors in incubators for babies. Okay, I'm not seeing much oxygen there at the moment. Okay, should we just give it a moment or two? There it is. I'm just going to try and tilt it towards you and get it to jump to the magnet. That's not working too well. Try underneath again. Okay, well what we can show you, just to prove that it's something there, and that is to demonstrate one of the most important properties of oxygen gas, and that's that things like to burn in it. It supports combustion. So the way we demonstrate this, and this is a classic test, a splint, okay? I'm going to blow it out, and with a bit of luck, it reignites, okay? One more time, blow it out, and it reignites, okay? So oxygen supports combustion, things like to burn in it.
Okay, yeah, I'm not too sure the oxygen magnet demonstration worked brilliantly on the video, but however, this is another kind of version of it. This is a photo we took on one of our other modules. This is liquid oxygen being poured between the poles of a magnet. You may know that the oxygen atoms in oxygen are held together by what we call a double bond. And in fact, associated with that double bond are two unpaired electrons, which act as tiny, tiny magnets. So you get this very weak form of magnetism they call paramagnetism. And there you can see your liquid oxygen being attracted into the poles of this big sort of iron magnet. You probably notice in the beaker where the liquid oxygen is a very pale blue color. That again is characteristic of liquid oxygen. So that was really a demonstration how we can make oxygen quite simply in the lab by condensing it out of the air. And another way of doing it is by chemically. So we've demonstrated the physical method. This is a chemical method. There's a chemical called hydrogen peroxide. Now I'm sure you all know water is H2O. This is a model. Chemists always like to make models because, as Mike said at the very start, atoms and molecules are tiny. You can't see them. However, we can make models of them. And this is a model of hydrogen peroxide. The two white balls are hydrogen atoms. The two red balls are oxygen atoms. So the formula is, as you might expect, H2O2. Okay. Now, hydrogen peroxide will break down naturally to form water and oxygen gas. And this actually forms the basis of a way of making oxygen. What I'm going to do, Mike, is just shoot onto the next slide and show you the classic demonstration. Many of you, and then I'll come back, yeah. And then many of you may have seen this, the old elephant's toothpaste demonstration, where you pour some peroxide plus some fairy liquid detergent of some sort, and catalyze the breakdown of the hydrogen peroxide using something like potassium iodide. And there we go. So, and you get a big oxygen foam, effectively. So that's a classic demonstration. What I'll do now, though, is scoot back and we'll show you something that's bang up to date, a completely different way of making oxygen.
Okay, so in March, NASA carried out an experiment on Mars, and this is called the MOXIE experiment, which catalytically converts carbon dioxide to oxygen. And that's because the Mars atmosphere is 98% carbon dioxide and 2% oxygen. And so they use a gas phase electrolysis, which is quite interesting because most electrolysis is in the liquid phase. And they heat it up to around 800 degrees, and they produced a total of 5.37 grams of oxygen. And you may say, well, that's good, why bother? Well, if man is going to travel to Mars, we're going to have to bring enough oxygen and enough carbon dioxide scrubber to remove the excess carbon dioxide. And there probably would be very difficult to take enough to go there and back. So the idea is that we go to Mars and we convert the carbon dioxide that's there to oxygen so that we can have enough to breathe and to power the rockets to send us back. So yeah, that's interesting. You can have a look on the NASA website for that experiment. It's quite interesting.
Yep.
Okay,
so back again to our peroxide decomposition. We know we've got an audience of chemists tonight, so no chemistry lecture will be complete without an equation or two. So Maria, do you want me to pass this over to you? There we go. I think you're mute at the moment, Maria. Yeah.
Sorry, thank you. So we have here another poll for you. Which of these two chemical equations is balance? Just a minute. This is an easy one. I don't know if
just
someone can tell me.
Oh, people are putting number 2, 2, 2, 2. A lot of people saying option 2.
Lovely. So if we can move to the next slide. Yes, the ones that went for option 2, that's the correct one. So we need to ensure that there is the same number of atoms of each type in the reactants and in the product. So in option 2, the number of hydrogen and oxygen atoms on both sides of the equation is equal, 4 hydrogens and 4 oxygens. So yeah, next.
Yes, so let's have a look at other uses of hydrogen peroxide. It was used in the early days of rockets as a rocket propellant. And so the V2 rocket used hydrogen peroxide to pump liquid oxygen to mix with the liquid hydrogen. It's also used in sterilizing water systems for prevention of Legionella's disease. And for those unlucky enough to suffer from diabetes, it's used in the biosensors which measure blood glucose. And you can see there's an example of a blood glucose monitor. And then finally, we made some hand sanitizer back last March with my colleagues in the laboratories, and we made a mixture of propan-2-ol, hydrogen peroxide and glycerine. And we made around 60 bottles for Milton Keynes Hospital, because unfortunately at that time, people were going in and stealing the hand sanitizers from the hospitals because there was a shortage. Okay, next.
Okay,
Rob,
so yeah,
combustion?
this is me, yeah. So we mentioned already that oxygen supports combustion or things like to burning it. So what's combustion? And we're going to show you a demonstration in a moment or two, taken from one of our lab casts. Well, combustion is the burning of something. It's a rapid chemical combination of a substance with oxygen involving the production of heat and light. And it's often kind of summarized as this sort of tetrahedron, the so-called fire tetrahedron. And those are the 4 components that you need essentially for fire. You need heat, you need fuel, you need oxygen, and you also need some sort of chain reaction. This is a chemical reaction that keeps itself going. It propagates itself once it gets started. Sometimes you actually just see this represented as a triangle with heat, fuel, and oxygen, but strictly speaking, it's heat, fuel, oxygen, and some sort of chain reaction. And coming back to one of the scientists who was involved in the discovery of oxygen, Carl Shaler in Sweden, he actually described oxygen as fire air. And this is a demonstration that we're going to do now. We're actually going to show you how to produce fire from water.
Rob is going to demonstrate that actually you can start a fire with water. So I'm quite intrigued with these chemical reactions.
Yeah, the first one is a little bit of a cheat. What we're going to do is add water to a compound that produces something that actually burns in oxygen. So this is something called calcium carbide, which is sitting there in the pie dish. And if you add water to it, it produces a gas called acetylene. So I just add a little bit of it. Oh, whoa, yes, that was a bit lively, to say the least, and that's warmed the room up nicely. So you see, the more water I add, actually, the more acetylene that's produced, and it's not that easy to put this fire out. You'll probably notice a few, it's actually gone out, that's good, soot particles floating around in the atmosphere. We'll come back to that in a moment. But I think we can make that a bit more interesting, can't we, Mike?
So, yeah, we can do. Are you going to get the splint
I'll get
on
the splint,
a bit of wood?
yeah. If you want to
so
explain
in the
it.
tin, we have some of our magic calcium carbide. I'm going to put the lid on. Whoops! Before I do it, I'm going to add a bit of water. Yeah, there we go. So add a couple of drops of water. Put the lid on quite firmly, and then Rob is going to use a fuse to ignite it.
Wow.
That was quite impressive.
Rob is going.
This is the chemistry involved there. Very quickly, another reaction for you here. Calcium carbide plus water gives you calcium hydroxide and acetylene. This is the gas that burns in oxygen really well. In fact, you can reach temperatures up to 3000 degrees C by burning it in oxygen, and this is used for welding metals together. So C2H2 is acetylene, and acetylene, but itself burns in oxygen. There you are, to carbon dioxide and water. And what we talked about in the lab cast, we commented on the formation of these soot particles. That really indicates that this combustion process is, to an extent, isn't complete, and actually you're producing carbon as well. Okay. Right. Let's show you another use of calcium carbide.
Yes, yeah, Rob. So in the early days of motor vehicles, the motor cars and motorcycles, they use calcium carbide lamps to produce, because they didn't have batteries in those days. So what you did is you put the calcium carbide in the base, and then in the top there is a water, and you adjusted a needle valve so that the water drop onto the calcium carbide, and then the acetylene then went through a tube into a burner, a little bit like a miniature Bunsen burner. And I bought this from a well-known auction site beginning with E, which I can't mention for obvious reasons. And I bought it for £20. Unfortunately, we couldn't get it to work properly because it was made in 1912, so it had a good life, I think. But it's interesting to see. Yeah, so the next thing we're going to talk about is explosives. So these are substances that rapidly release energy, usually as heat, with the production of large quantities of gas. So it's a rapid, uncontrolled reaction. And these comprise of an oxidizing agent and a fuel. Sometimes they're built into the same molecule. And we go back to our old friend potassium nitrate, which is one of the components of gunpowder, or also called black powder. The other components are sulfur and carbon, like charcoal. So these burn to produce large amounts of nitrogen, carbon dioxide, and smoke. And the first person to bring it into Europe, although it was discovered by the Chinese originally in around 800 AD, and the Arab nations got the recipe from the Chinese in around 1000 AD, and Roger Bacon found the recipe. Unfortunately, he had an argument with the Pope at the time, so he tried to keep the formula a secret. So this is his code, although he wasn't a particularly good code breaker, because you can see the word saltpeter if you look carefully. So anyway, he said, of saltpeter take 6 parts, young willow, which is charcoal, and 5 of sulfur, and so you will make thunder and lightning. And so we should have a video, some stills of me. So I made some gunpowder in the laboratory. I do have an explosives license, by the way, just in case you're worried. And we can see we had a fuse from an old firework, and indeed we did make thunder and lightning. Okay, next. You're on
So
mute.
in the next video, we are going to discuss chemical reactions that do the opposite from the exothermic reactions that we've seen so far. We're going to look at chemical reactions that take energy, take heat from the surroundings. So let's watch the clip.
All the chemical reactions that we've been looking at are exothermic, so the heat is produced. But this is not the case for all the chemical reactions. So Rob and Mike are going to demonstrate now a chemical reaction that actually takes heat from the surroundings.
Oh, I was going to use. Okay, so this is what we're going to do. We've got two white powders here. This is barium hydroxide, and this is ammonium thiocyanate. Don't worry too much about the actual compounds. We'll come to those in a moment. What we're going to do is, well, first what Mike's doing, you'll notice, is adding a bit of water on top of this wooden block. Again, all will become clear in a moment or two's time. And there's our beaker. So that's our reaction vessel. Now let's add, do you want to have a look at the equation first so we can see what we're going to do? There we go. Barium hydroxide. If you don't like using formula, then just look at the word equation below. Barium hydroxide plus ammonium thiocyanate gives you ammonia, water, and barium thiocyanate. Okay. Note the ammonia gas. This is a bit of an issue for us, as you'll see in a minute. Let me add the two ingredients. Okay, they both go in. And what we're going to do is, so it's very difficult to see anything actually happening yourself, I guess, but if I start to stir it, starts to become, there's a lot of water in these compounds, it all becomes a bit of a slurry. We're not quite, can I? Yeah, not
ready yet.
It's just started to react, and one thing we can't convey to you at home is the awful ammonia smell. Now ammonia is, maybe we did use a different bit of paper actually, that's already changed, I think. Yeah, okay, great. Ammonia is an alkaline gas, and what Mike's going to do is hold some indicator paper just above it there, and you can see a nice...
It changes,
nice. Do you want to dip it in a bit further? Maybe we'll get a bit more. Great.
Yeah.
I think that's definitely gone.
Yeah.
A bluey-green colour.
Bluey-green, yeah.
And my fingers feel the reaction is very cold, and with a bit of luck, you remember that we put the water underneath. This is the fingers crossed moment. If I actually grab that there, oh yeah, it's worked. We can actually raise the wooden block. So the water has converted to ice, so cold it's changed to ice below the beaker, proving, I think, without doubt, that this is an endothermic chemical reaction.
So, okay, we have seen now examples of exothermic reactions producing heat, endothermic reactions taking heat. And next, in the next video, Mike and Rob are going to demonstrate another type of chemical reaction, a chemical reaction that gives out light, a phenomenon known as chemiluminescence.
Can you demonstrate for us a chemical reaction that doesn't involve changes in heat?
Yes, I can, Maria. And if we have a look at the equation, we have in one of these, I have luminol, which is the chemical you see there, and in the second one, I have bleach. And when we mix the two together, we get oxidation due to the bleach, and we get products and light. Now, we're going to have the lights down a bit. Okay. And you can see. So this is the basic chemistry behind the chemiluminescent, the glow sticks and that you might see at fairs and festivals and that. And if you feel it, there's no temperature change. So it's not warmed up and it's not cooled down. So it stayed exactly the same. Okay, so we're coming towards the end. And I'm going to talk about how we can use clever chemistry to save lives and use some of the chemicals we've talked about before. So this company, Semco, was asked to develop a self-contained breathing apparatus as a way of escaping from burning buildings and burning laboratories. So what it contains, you can see our model here is modeling So you put it over your head and you start to breathe. And it's called Head 10 because it gives you 10 minutes of breathing oxygen. And it has a little timer in it, and it beeps to tell you that it's working. And then after about 7 minutes, it gives you a couple of beeps to say, right, you've got 3 minutes to get out of the burning building, and then all of your oxygen is used up. So you can see what happens is there's a chlorate candle which burns and produces oxygen in a similar way to our mercuric oxide that we had before. But obviously chlorate is a lot safer than mercury. So you breathe in the oxygen in this counter lung. However, what we breathe out is carbon dioxide. So we need to remove the carbon dioxide. And here's where the clever chemistry comes in. So the carbon dioxide and water reacts with potassium superoxide to produce more oxygen and remove the carbon dioxide. Go on to the next slide. So you can see KO2 plus CO2 gives you potassium carbonate and more oxygen. It also produces hydrogen peroxide, which, as we've shown earlier, further breaks down to water and oxygen. So this technology is now being used in aircraft. You know, when they say that the oxygen mask will drop down from above, that technology is used in aircraft now, especially because we want to save fuel. We want to make the aircraft as light as possible. Whereas in the old days, they used to carry oxygen cylinders, which are very heavy. Okay, next one.
So finally, finally, we would like to encourage you to discover more chemistry. It is great fun, and there are lots of experiments that you can even do in your kitchen. No need to use hard to find chemicals or sophisticated equipment, but please always consider doing science safely before embarking on any experiment. And we would like to also invite you to visit the OpenLearn website. That is the home of free learning at the OU. Yes, free online short courses, and not only in chemistry. And if you enjoy studying online and want to know more about studying a chemistry degree at the Open University, please visit our website. It would be great to meet many of you again in a few years' time. So yeah, thank you for coming. And if we have time, we could ask any questions that you have.
So thank you very much, Maria, Robert, and Michael, for that excellent presentation. And although it's a shame we can't be in the lecture theatre, thank you very much for recording those videos. They're very, very effective. So thank you very much for that. I'd certainly echo the comments about doing simple experiments at home. In fact, that's where my passion for chemistry came. When I was a child, I used my electric transformer to electrolyze water and copper plate my mother's crockery and this sort of thing, cutlery rather. So yeah, do experiment. And I think I had a book at the time, it was a Ladybug book called Magnets, Bulbs and Batteries. And yeah, do experiment. There's a load you can do actually in the kitchen as well. And as shown earlier, the Open University have a wealth of ideas. So thank you very much, everyone. As I said, they are taking questions. So if you wish to have any questions, please put them in the chat and we can answer. So a few people are saying thank you very much already. In fact, one of the questions I was going to ask you answered when you talked about the chemical production of oxygen. I was going to ask whether in aircraft, when the masks come down, whether that is pressurized oxygen or a chemical reaction. So there you answered that, and I guess that's because of the weight there. But in those typical systems, how long can actually produce oxygen for in a typical system? Do you know how effective they are?
Well, the one that is used as the first one they developed was called the Head 10, but they're now onto the third generation, which is the Head 20. So that will give you 20 minutes of oxygen. So in the case of the aircraft, then obviously if it loses pressure, then the pilots are going to try and get as low as possible because they want to get back to atmospheric pressure. So they hope that they can get the plane as low as possible and you know, in a good result of landing it. And as a film showed once that this guy managed to land it on the River Hudson in New York. That was quite impressive, to land the aircraft there when when it depressurized.
Absolutely. I mean, 10 or 20 minutes doesn't sound a long time, but if you're trying to escape a burning building, that is
it is, yes.
So long.
You want to get out. I mean, the big problem with the fire is that people actually die because the flames use up all the oxygen and they can't breathe, and that the smoke gets into their lungs and causes, you know, severe lung damage. So by having the self-contained breathing apparatus, you're avoiding getting any smoke in your lungs as well.
Excellent, thank you.
Yeah.
Thank you for that. Any other questions from our audience? Please do feel free to put them in the chat. I don't know who else can see the chat, but I'm looking down here. Uncharacteristically, we have quite a quiet audience tonight. There's normally loads of questions. Or maybe they're all rushing off to do some experiments in the kitchen sink.
Or maybe to watch the football.
But actually, if I may, obviously the Open University has always been known for sending out equipment, as you say, to do the experiments at home. Do you think after the last kind of lockdown, do you think we'll see an increase of people doing sort of distance learning from home? Have you found a sort of increase in applications, or is it too early to say at the moment?
Well, we have to say that we've actually done very well out of the COVID in some ways, but in other ways we have had to close down our some of our summer schools. And in fact, what we've done is produce home experiment kits for engineering students as well. And we've tried to increase the number of home experiments, and we've got a couple of Nuffield students who are helping us this summer to develop the next generation of home experiments. And we're going to try use technology such as smartphones, and you can, if you're clever, you can actually set them up as a colorimeter to do some colorimetric type analysis. So that's what we're trying to do.
Well, that's amazing. I mean, I also saw, I think it was a chemical education journal, of how you can make a Lego spectrometer. It's quite impressive what you can do these days.
Yeah, that's right.
And I was also very impressed how you can actually have remote control to some of the lab equipment as well. Is that quite difficult to set up, or how do you sort of monitor the access from students to your equipment?
Yeah, that's a challenge. Yeah, there's two challenges in that. Is firstly is to the security aspect. So basically, again, only students that are registered with us will have access, and we have a special server that it runs on, so it's apart from the rest of our systems. So it's very difficult for people to hack into it, which gives us the security. The other thing is that most of the modern instruments have very sophisticated software, and students aren't going to spend, 2 or 3 weeks learning the software for a 1-hour experiment. So this is where we have our own software engineers that built a simple interface. And you can see, do you want to go back to that slide, Rob, just to show right at the beginning? Yeah, this one here, you can see this is our sort of patented interface for these experiments. And so that's what the student sees. So that it also protects our instruments as well, that they can't they can't do things to break it, because we only allow a certain controls of certain functions. So yes, yeah, that's how we do it. And we are very fortunate to have an excellent software engineer who, if he can get into the instrument's own control software, then he can write a control program to do it. But we have found also that some instrument manufacturers are difficult to access, shall we say. They don't want to give their secrets away.
Yeah, I can imagine.
Yes, yeah, so licensing, but I mean, we do obviously, we are willing to set up non-disclosure agreements with them to protect their software as well. So we're not making it open to everybody.
But that's a great GUI that you've got the data, you can see, you can control the instrument, but you've also got a webcam as well, so the students actually see visually what the instrument's doing. That's
Yes.
Excellent feedback, isn't it?
That's right. Yeah. So they actually see it happening, which is that's the thing that's unique. We do know that our competitors are working on it as well. So yes, yeah, it's going to be the big thing. I predict in the next sort of 5 years that a lot of universities are going to be doing remote online experiments like ourselves.
Wow. Excellent, thank you very much.
Yeah.
So you're on mute, Trevor.
Yeah. Unmute yourself.
Slow.
Can you hear me now?
Yes,
Yep,
we
there
hear
we
you
go.
now. Yeah.
Okay. Have you seen this article in the RSC magazine called Education in Chemistry? It was in March.
Is that the latest
It's
edition?
in March this year.
Oh, okay.
And what it shows you how to do the Beer-Lambert law using something like Ribena.
Yes, yeah.
What you have to do is put on your phone an app. I've got on my phone one called Lux, which measures light intensity.
Yes, yeah. We're doing something similar like that. I'd say we've been looking at beta carotene, which is the one that you can do. I've also been looking at, demonstrating chromatography, separating food colors with a solid phase extraction cartridge, which is like a miniature chromatography column. So that's another one that we're working on.
Can you use something like corn flour or cornstarch to do that as the solid phase?
You could, but
in through the top.
Yeah, the thing is that then, I mean, these solid phase extraction cartridges, they're already prepared, and so they're not too expensive. They work out about £2 each. So we can afford to send them, and then they can use things like ethanol or propantuol as the elution controlling solvent, so they can get the different colors off.
I remember the good old days of having a chemistry club at school, and we used to use an old-fashioned stick of chalk standing in a petri dish of coloured liquid, and it would just simply soak up and separate.
Yes, yeah. So that was, well, I mean, that was the original chromatography experiment with the Russian Svet, and he used calcium carbide. So calcium carbonate.
Not calcium carbide.
Calcium carbonate. and he used petroleum ether and separated the chlorophyll pigments on it. So that was the first ever one.
And when we moved over to dustless chalk, the whole thing was ruined. You couldn't do it.
Yes, yeah.
What made it dustless?
I think
was it like a coating on the outside, is it?
I think it was like chalk mixed with a greasy material.
Yeah, I remember the texture was completely different.
A bit like a Crayola.
Yeah.
Any further questions from anybody? Or any questions about the Open University or from our presenters?
I was interested in the Mars experiment with Moxie.
Yeah,
Yes,
that was,
yeah.
wasn't it? Very topical.
Yeah, if you go on the NASA website, you can download that. It's very interesting.
Are they thinking of terraforming Mars?
Well, I don't think they'll ever be able to make that much, but they're hoping to make enough to sort of replenish what they've used from their stocks. So that's the idea, because if you think about it, it's going to be somewhere in the region of 2 to 3 years, and to take that amount of oxygen is going to be a challenge. I mean, one other suggestion is to create a whole ecosystem so that they're recycling everything, so that they are recycling all their waste products and then growing their own food and then eating it, recycling it, using the plants to absorb the carbon dioxide and generate the oxygen. So yeah, it's going to be a major challenge.
So you've seen the Matt Damon film called The Martian?
I have, yes. Yes.
Growing his potatoes in you know what?
Yes, exactly. Well, they're going to have to do it. Yes, yeah, yeah.
Well, we don't have any argument with using farmyard manure, do we?
No, exactly. And I think it's only because that you know, unfortunately, we can't clean up the sewage sufficiently. Otherwise, we would use it on our fields, and they obviously they use farmyard animals, pigs and cows and that to spread on fields to fertilize them.
Well, I know that in the Birmingham area, the big sewage farm, which deals all with Birmingham waste, generates its own methane and is self-sufficient.
Yes, yeah. Well, that's
impressive. Yeah.
That is one of the major uses, that you know, you can collect the methane and generate your own electricity. So,
I think he was in one of the Mad Max films, maybe the third one, Mad Max and the Thunderdome.
Oh, yeah.
I think you watch too much television, Trevor.
They were using pig manure for that.
That's right.
You know this Moxie experiment. What kind of a process is it? You said it was catalyzed. Is it an electrolysis process?
It's a gas phase electrolysis that's taking place at around 800 degrees. So it permeates through some sort of catalyst, which is obviously designed with a pore structure that allows the gases to permeate and react at the same time. So it's quite novel technology, because
they could use solar cells to generate electricity.
Yeah. They would have to use the solar cells to generate. I mean, that's what they do on most of these you know, planetary class. They use solar cells. The only exceptions were the ones, you know, the Pioneer that went out into the that left our solar system. There they use plutonium to generate electricity. Obviously, because they were so far away from the sun, they weren't going to get any solar power from that.
You've just taken me back to the Martian film again, because he finds the plutonium there, doesn't he?
Yes.
Keeps your hands warm.
Yeah.
I think that was the whole idea.
Yeah. Okay, well, I hope you enjoyed this evening, and let's hope in 2 years' time we'll be able to see you live.
Yes, thank you very much. Thank you.